Before we go to the second topic on dynamic programming, we take a look at another important concept that you will need to know when it comes to software engineering. That is design pattern. In life, there are many problems that can be solved with programming or algorithmic paradigms. It is the same for structuring those actual coding we write. There are often many ways to achieve a goal, but there are good ways to write or structure our code to help to build cleaner and more maintainable systems. That is the role of design patterns. A design pattern is a reusable solution to common software design problems. Software here means the way that you write your code. In computer science, all these years, we have developed many design patterns. There is a famous book on design pattern by the Gang of Four. You can find that in Google search. For us, we see a particular design pattern called wrapper, or also called decorator. It is a design pattern that attaches additional responsibility to a function or to an object in the case of object-oriented programming. So given the function performing something, we don't want to change much of its coding, just want to wrap it up by a wrapper to do the original work plus more. In the previous video, you saw we needed to amend the codes at two places to perform the memoization, and we did it in the same ways for all the three examples we had. Here's a design pattern that allows us to achieve it without having to amend our codes in some ways using a particular design pattern called wrapper. We're going to see three presentations of using the wrapper. The first two are with no change to the original recursive codes, while the last needs to change the code with an additional helper function. Indeed, the last one is just for illustration, and usually we don't do it that way in practice. We now see the detail of our memoir function, which is our wrapper. This is going to be used by all the three presentations. A memoir function is a function that maintains a table in which values of previous calls are stored. It uses the arguments that produces the values as keys. When the memoir function is called, it checks the table to see if the value existed. If so, return the value. Otherwise, compute new value in the usual way and store it into the table for future use. Here is the detail of the codes. Memoir table, which is a dictionary of dictionary, and each dictionary is for a function that we want to do the memoization. Define memoir, it takes in a function. It checks the name of the function from this built-in system call to get the name, and it checks whether this name has been called before in our table. If not, we have to create this new table, which is a dictionary in the dictionary. Then this table is our memoir table for this particular function. In future, when memoir is called, this helper function will be run, and it checks if the arguments to this helper is already in the table, which is this argument is the key. If so, it returns the value as computed previously. Otherwise, it takes the argument and apply the function to get the result and store the result into the table, then return the result. So this achieves the goal of computing it when it's not available, using the value in the past if it has already been known. This is exactly the kind of stuff that we added to our recursive function to remember the past values and use it if available to the present calculation. Now we see how this is applied to our first example, Fibonacci. This is the original code. So to use memoir, the obvious thing to do is to define memoir fib equal to calling that function and passing Fibonacci into memoir. Actually, this is wrong because the Fibonacci here will still call the Fibonacci instead of the memoir version of the Fibonacci. So the correct way to do this is to write Fibonacci is equal to memoir Fibonacci. So this override the original fib, and when the call comes in, this Fibonacci will indeed be the same. So the whole code will look like this. This is the original one with the Fibonacci equal to memoir Fibonacci. So this is version 1 of our presentation. Now with this Fibonacci, as I said, you will use the Fibonacci from this memoir, and the thing will work out that the algorithm will no longer be exponential in time, but linear to the size n. Now we see the second version of Fibonacci. This is the original wrapper. The memoization will look like this. This is to use the decorator, ampersand, memoir, and the code remains. So this actually means that the function Fibonacci here is passed as an argument into this parameter f, and all the f are replaced by this Fibonacci in this code. This achieves the same goal as the previous presentation with ampersand memoir as a decorator. So the time complexity is again linear to the size of n, and this is assuming the table lookup, which is here, and the return the value, it's also O of 1 to achieve the overall O of n, where n is the input number to the Fibonacci function. Here's the third presentation, and in this case, it is a change to the original code with an inert function, which we call Fibonacci helper in here. So this is the original code, and this original code is intended to define a helper. The memoir is written directly in here. So as I said, this presentation is not usually used as compared to the more convenient version of using a decorator in the previous presentation. Now the question is, if this is changed to Fibonacci helper as this helper, would this code work? You can find it out by doing that yourself. Now here is another example, our example 2 on n choose k. For the first presentation, this is the choose original function. We just simply have to write choose to override this to be the memoir of choose. Choose as a function into memoir wrapper. The second version, we keep the original code also, but we just need to use the decorator syntax ampersand memoir to treat this to pass into memoir. For the third version, we indent our original code to become our helper function, and we call the helper function with the memoir. The time complexity is n times k, the same as what we saw in the previous video. For our last example on chocolate packing, this was the recursive code on pig. Here is our memoization. We just present version 3. In this version 3, we indent the original code to be our helper function and call it with memoir, and we are done. As for the other two versions, you can work them out very easily. So just a quick recap on memoization. What we do are two steps. First, we write the function to perform the required recursive computation. Second, we use a wrapper that can store and retrieve the result of previous calculation, and the lookup is assumed to be constant time.